I'm Tom. I work for Dynatrace, one of the partners of this meetup. And today, as I already said, everybody wants to find security bugs in an automated way in their software. And there's lots of products out there that claim that they can find all of them or many of them. And so they claim that they cover the OWASP top 10, which I'm not sure if this is true. Well, I'm actually sure it is not. We will have a closer look of why this cannot be true and what would be a more sustainable approach. Very quickly about me, I'm a software security architect at Dynatrace. I do stuff like, for example, threat modeling. I manage security bugs. I do process improvements for software developers with regard to security. I try to build awareness of security problems. I'm also a hobby barista, so I hope there are any coffee nerds out there as well. And I also try to automate my home as much as I can. And yeah, this is me. So what is the agenda for today? I'll quickly talk about why we're here and why we're talking about this topic. Then I will go into vulnerability dimensions. So we will have a look at, for example, the OWASP top 10 and try to classify and categorize those things a bit. It looks like a one-dimensional list, but in fact it isn't. We will have a look at 3 tool types, so automated tooling, and I will quickly explain the differences between the 3 types of automated tooling. There are others, but these are the most, let's say, most established 3 ones. And we will see that covering vulnerability classes like the OWASP top 10 is really hard or probably impossible to do with automated tooling only. So I will present a more sustainable approach if you want to go about covering those, let's say, OWASP top 10. Could be another list as well. And at the end, I'll quickly wrap up. So why are we here? We hopefully, when we create software, we also have software security activities. So we do code reviews. We have maybe external penetration tests. We hopefully have some tooling. We build awareness for developers. We have some process steps implemented that make sure that our software is secure. So why are we doing all this? Well, there is some degree of customer expectations, because if we sell the software or we run it as a SaaS platform and customers use that platform and push their data in, they expect that their data is safe in there, right? They expect it not to be stolen. This is a company expectation. Like, for example, the company wants to be able to tell the customer, look, this is what we do in terms of security activities, so that it's more likely that they buy our product, right? There are also compliance reasons. There's things like specific laws and regulations that apply to certain sectors like finance or automotive, whatever. And so we must comply with some security rules there. There's hopefully also some intrinsic motivation, because we're all engineers. We want to build perfect products. We want to create good software. And good software means not just functional, but also non-functional requirements, such as security, right? Also accessibility, maintainability, all those entities that we want in there. Okay, so what exactly are the demands? This is often unclear. It's not so easy to say this is what we want in terms of security, because the threat landscape is just really big. But there are some commonly used lists of vulnerability classes out there that are often mentioned in this regard. So a company could say, we want to protect ourselves against the OWASP top 10, or the OWASP API Security top 10, which is something similar, but for APIs specifically, so not for classic server-side rendered applications where request goes to the server, HTML is built, whole HTML gets back and is rendered by the browser, but single-page applications, for example, that speak with a JSON REST API, for example. So let's have a closer look at the OWASP top 10. I have to have the prerequisite that you know some of those things. I'm not going to explain all of them in very much detail. This is beyond the scope of this. But here they are in the version 2021, so they came out last year. There are things in there like broken access control, for example. So you could issue a request, and although you're not administrator, you get back admin content of that application, right? Injection is a very popular one. You might know SQL injection. That's a historic one. Hopefully, soon solved problem, not yet fully solved. There's a new one in the OWASP top 10 2021. That's insecure design. I find that one particularly interesting because it's not a vulnerability that relates to code. It relates to how you set up your software. So it's stuff that happened while you were drawing on the whiteboard, right? And so on and so forth. So this is the OWASP top 10. I will have a bit closer look at some of those. There's also the OWASP API Security top 10. So if you're creating, let's say, a REST API for your smartphone app or for your single page application, there's a dedicated list for this specific type of software. And I really recommend you to have a look at the OWASP API Security top 10. There are a few new ones in there. For example, API 3, excessive data exposure. This is when you have database tables or objects, and let's say you have a user object that has first name, last name, email, and a few other things. And instead of selecting the fields that you give back from an API, you push back the whole serialized object, including password hash, role, everything. That would be an example of excessive data exposure. That is specific to APIs. The other way around, so being able to push in data from the outside that's not supposed to be done by the API, but something internal, is API 6, mass assignment. So that's the other way around, when you don't selectively take out form fields and assign them to, let's say, a row in a database. So I have merged the two lists into Tom's top 13 because many of those are the same. So looking at the first line here, you see broken access control, broken object level authorization, broken function level authorization. They're basically the same category of bug. They are an access control problem. Right? Both have injection, for example, the OWASP top 10 and the API security top 10. So I've summarized them, and so altogether it's 13 security bug classes that we're looking at. So let's suppose your company says, we want to protect ourselves against these 13 problems, right? Looking at this list, it looks like a one-dimensional list. It looks like something, I take the first problem, I look whether I have this problem, maybe I take automated tooling, I'll fix the problem, and I'm done. I can check the box and I can hop on to the next. But I can tell you it's not one-dimensional. So there are many aspects that are different for each of those bug classes. Let's have a closer look at those dimensions, I call it. First, a little exercise for you, okay? Let's suppose we have this request in our web application. It goes to an API, let's say, and it's a web shop where you can list your orders that you made. Okay, this is the corresponding API code, the backend code. It's a Spring controller that reads the order out of the database. So it's going to throw an exception if you're not logged in. It's going to go to the repository and find the order with that specific ID, and it's going to return that serialized version of that order back to the calling application. So the question is, where is the security problem in here? I know you can answer back. That's a little bit of a pity, but I'll give you, let's say, 10 more seconds to look at this code and to see whether you can find the security problem here. You got it? I hope you did. Because what an attacker could do is they could just iterate through the numbers 1 to 1,000 and read out orders also potentially with other people. Because the checking here just says whether I'm logged in or not. It doesn't check whether that specific order actually belongs to me. It could be an order of some person on some other person. So 5264 is my order, but 5263, the previous one, was not done by me because I did 2 orders in a row. I did not do 2 orders in a row, but another person did that before me. So that's a huge confidentiality problem because I can read data. If that happens to big web shops out there, they are in the newspaper if someone attacks them. So that brings me to the first vulnerability dimension, so to say, error proneness. So the question here is, how easy is it that the developer introduces this bug? Okay, how easy is it to spot the vulnerability? Because that code didn't have, from my point of view, something really obvious where you could say, oh, this is a problem here, right? You had to think, you had to look longer. Most of you probably, I don't know, I had to look longer when I saw this the first time doing a code review. So how much awareness is generally there about this bug class? How likely is it that this error happens? So the error proneness for this specific problem that you could see in the previous slide, it's called insecure direct object references or missing object level function, missing function, object level access control. That's really easy to confuse. That has high error proneness. There's nothing that protects you against this automatically, right? Like with SQL injection, you have object relational mappers that do prepared statements automatically. So if you use the framework in the right way, you're basically done. In this case, there's nothing to protect you. For SQL injection, as just mentioned, everybody knows the problem. Most developers know what SQL injection means. There are frameworks that protect you against that, so the error proneness is pretty low here. So this is very different for each one of those 13 bug classes. Technology support, another dimension. So how good is the protection by default in common tech stacks? So look at frameworks like Ruby on Rails, PHP Symfony, Java Spring, Python Django, take whichever you want, ASP.NET Core, and does it protect you against insecure direct object references, for example? I don't think it does. I don't know any framework that has out of the box by default protection. It really is not possible if you think of it, because the framework can't know whether this is a public endpoint or if I need to do object-based access control. So this is really up to the business logic and the requirements of the software. So if there are any protection mechanisms, how easily are they bypassed? If we look at a specific vulnerability class called lack of resources and rate limiting. So it is advisable to have some sort of rate limiting. For example, if users log into your system, they could also do brute force or dictionary attacks, guessing passwords. So there should be a limit. They shouldn't be able to do that in an unlimited way and be able to browse through millions of passwords for specific users in order to guess their passwords. Right? So there should be a rate limiting on this. Technology support for this is really bad. I don't know of any web framework out there that has automatic throttling built in. So there might be external libraries. There might even be a framework, I don't know. But the common ones, as far as I know, don't have that. XML external entities, however, is a problem where the XML parser processes an XML document in a way so it can read local text-based files from the file system of the server if the XML is originating from the outside. So in the text, so for example, inside an HTTP request. That's a really bad one, but technology support is really good because almost all of the XML parsers out there, I know, by default, turn off the functionality of the parser that enables this attack. So it's really hard to get it wrong because technology support is really good. An important aspect of what I mentioned is automated testability. So how reliably can automated tools find that specific security bug class? Are there common tool types out there that support it? Let's have a look at a concrete example, broken authentication. Broken authentication is a very broad class because it can, there can be many things can be broken in an authentication scheme. It could be username and password with, I don't know, a wrong password or a bad password policy. It could be brute force attacks. You can do a dictionary attacks. It could be your OpenID Connect integration wrong because you don't do signature checks, or you can repeat authorization codes. Hundreds of things that can go wrong with broken authentication. So the automated testability is really bad. There's no reliable way to throw source code at a tool that does authentication that reliably tells you all of those problems. It's just impossible. It's just so broad. However, if you look at TLS configuration, protection in transit, and the cryptographic algorithms that are used with TLS, there are good tools out there that can reliably tell you that for which browser or which cryptographic algorithm will be chosen and whether that's a good one. That's really, there's good tooling out there. Automated testability, really good with TLS. Another dimension is manual verifiability. So if a human being looks at the code, can they detect reliable whether there's a problem or not? Also, how distributed is the information needed for that verification? Is that one line of code, or do I have to look at both configuration of my server and my web server and my Kubernetes cluster and my AWS account and blah, 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 in order to see whether this is a problem? Or, really bad in this regard is insufficient logging and monitoring. So this vulnerability means I have no visibility. If somebody tries to brute force my password, I don't even see that somebody is trying that. So nothing is logged, nothing is monitored, there's no alerting, and so on and so forth. Manual verifiability, whether there is sufficient logging monitoring, is really hard, because first I have to look into application code, whether it's logged. I have to look into the, I don't know, logging tool where the logs are collected. I have to look at the alerting mechanisms, whether an actual alert is triggered in that case, and so on. So this is a whole chain of things I have to look at. Excessive data exposure mass assignment, remember, requests going in and out where too much data can be either set or read out of the database behind it. That can be manually verified, because if that, that database implementation object, that entity, is just directly serialized without any layer in between, I can see at first sight that there is a problem. Stack distribution. So how distributed are the relevant aspects over the whole stack? Can I see all the relevant bits and pieces? So that's hardly linked to the manual verifiability. Again, insufficient logging monitoring. In order to verify that logging, monitoring, my software are well done, I have to look at many places in my infrastructure. And that's really hard to tell. Insecure deserialization, you might have heard that one. So imagine a web application where you send serialized objects from the front end, so from the untrusted source, potentially an attacker, into the application. There was an example, I think, the Java myfaces view state. I think there was a serialized Java object that was sent by with every post request that was sent from the front end. And an attacker can manipulate this object so that in the backend there are actions executed, the actions that the attacker wants. That could lead, the worst case would be remote code execution. We saw that in the past. So that stack distribution with this one is really low, because deserialization happens in one spot in my source code and not in many different ones. Also, a big factor of bug classes dimensions is the availability of defense in depth. So are there any good second layers of defense that I can use, that are ready to use, that are well supported by technology that I use? And can it be implemented easily? So looking at a bad example of availability of defense in depth is, again, broken authentication, right? I think of, you might know, some of you might be registered with one of the big service providers like, Google, Apple, Dropbox, whatever. So when you log in from a new device for them, you get an email notification that says log in from a new device. And that's a good defense in depth, because if something bad happens, if somebody takes over your account, at least you notice and you can do something about it. So that's a second layer of defense. You suppose that bad stuff already happened, right? This is not just ready-made available in any of the tech stacks that I know, in any of the web frameworks that I know. So this is something you need to do on your own. A good example for availability of defense in depth is cross-site scripting. Cross-site scripting being an attack where you manage to execute code in the web browser of other users. So that could be something, let's say you have a messaging application, you can write messages to other people, something like Slack or something similar. And you could not just write messages, but also JavaScript code into the message, and it doesn't get encoded on the other end, so that instead of being shown to the other user, it gets executed into context. That's a pretty common problem in web applications. There's a good defense in depth for cross-site scripting. If I had a crowd in front of me, I would ask who knows what that is. So you had 15 seconds at least to think about it. It's the content security policy. That's a really good defense in depth. You can look it up, or you might already know it. Also, a vulnerability I mentioned is versatility. So how narrow is the definition of that bug class? Broken authentication, again, is very broad. There could be hundreds of potential specific problems in there. So can it have different characteristics in general or in specific environments? So high versatility, which is bad for automated testing, is security misconfiguration. Security configuration of a framework can be anything. It can be the TLS configuration. It can be cookie flags. It can be cross-origin, of course, cross-origin resource sharing settings. It can be, I don't know, the XML parser setting, whatever. It can be hundreds of different things, and that's very specific to the environment that you're in. So high versatility here. Where do we have low versatility? For example, using components with no vulnerabilities. That's a very narrow definition because it says you're using a component that has a known vulnerability in there, and you should update that library you're using. So that's pretty easy explained, as opposed to security misconfiguration that can be everything. Also very different dimension of security bug classes is the place of best mitigation. So where do we fix the problem best? It could be implementation, ideally. I change a line of code and I'm done. I change a configuration. Let's say I have a weak TLS cipher configured. I go to my reverse proxy or whatever TLS offloading component I have. I put out that cipher because I might realize I don't even need it for backwards compatibility. I have mostly newer browsers. So I can just change the configuration and I'm done. So that's implementation or configuration. But there could be a problem that I have to fix in the design of the software. So I have to go back to the whiteboard and think about how can I fix this problem. And specifically, authentication, authorization bug classes tend to be very design heavy. So let's say I have a login with username and password, and it's really weakly designed. I have no password hashing in the backend. I have no password policy. I have no lockout mechanism. I'm not protected against brute force attacks. I have no transparency. I cannot delete sessions and devices. None of these things are there. So I decide to have an external identity provider integrated into my software, right? I can say, let's log in with Microsoft, or let's log in with Google, or let's log in with Facebook. And that would be, I have to integrate my OpenID Connect would be a classic example. So that's a design, that's not implementation. I have to, that's a conceptual thing, whether I want to have the usernames, passwords in my own database, or I want to externalize that responsibility. It can also be a process thing, because let's say we ship a software and then a customer complains that we're not meeting the GDPR requirements. If that was the case, I can just go into the source code, change a line of code, and that's fixed. Not even 10 lines of code. I have to think about how could I miss that? So there's probably a step missing where I think about compliance requirements. So during the requirements engineering, I didn't think about external laws, regulations, and so on that are important for the type of software that I'm doing, right? So if a problem in that regard turns up, I probably have to change something in the process, in the way how I create software, not in a line of code. Also, the question in the place of best mitigation is there just one place where I can fix the problem, or are there many places? So a typical example of many places is function level authorization, right? So the classic example would be you have a web shop and you as an end user, you can place orders. So you have to role with an end user, a non-privileged role. And then you have administrators that can log into the platform. They can change orders. They can update order states and so on. So they have high privileged access. That authorization ideally is just in one place, but that's usually really hard to do. So mitigating access control problems usually is a question of there's some piece of access control somewhere in the controller, somewhere in the data access layer. There might be some access authorization be done even in a database, so many layers where I have to mitigate the problem probably. Cross-site request forgery is a very specific problem. So for web browsers, let's say you have two applications open. One, you're logged into your e-banking account, and the other one is you're logged into, or you clicked on the link of a malicious person who sent you an email. Then another tab goes up, and there's one thing that web browsers are still susceptible to. You can do cross-origin posts. So that attacker.com website, let's call it that way, has a form embedded that targets the bank, that creates a transaction, and it automatically hits that submit button. It's going to do a cross-origin post request. It's going to be authenticated. Right? That's that one hole in the same origin policy. Everything you can do with web forms, you can do cross-origin as well. Right? It's a simple request, even though it's a post request. I looked it up. The Mozilla Developer Network documentation on that is really good, on coarse and simple and pre-flight requests. So it relates to this problem, cross-site request forgery, but you can fix it in one place. You can say in every non-GET request, you send a random token that's specific for your session, and you check for the presence of the token in the backend. One place, 1.5 places to fix. Place of best assurance. So assurance means not just fixing the problem, but making sure that it doesn't turn up again. So how can I assure that these mitigations are really effective? Is there one place where I can make sure that this happens, or are there many half-baked ones, right? Is it static analysis I should do, or dynamic analysis, or software composition analysis, or a unit test, or room? Many different places where I could do assurance. So doing it right is one thing, but checking whether I really did it right and didn't miss anything is another thing. It's called assurance. Broken authentication, an example of a negative example again here. It's really hard to make sure that everything is right in there. Many things are already heavy on design and architectural questions. So there could be many different places where I have assurance. Using components with known vulnerabilities can be one place. So I can have, for example, software composition analysis that does dependency checks. In my pipeline, at every commit or every push, I start my SCA tool that checks for known security problems in the libraries that I'm using. Okay, so summing up this, the vulnerability dimensions, it's not one-dimensional. Looking at the list of all the top lists, they are completely different problems. They are not comparable. It's not that you can say, I take one tool to rule them all, to fix them all, to find them all. That's not possible, as you have seen right now. So if somebody claims that this is possible, it usually isn't. Right? So in terms of how error-prone is the problem, how's the support of your stack or of your framework? How good are tools, automated tools, at reliably detecting the problem? How well can it be verified by a human being? How distributed is the problem through the stack? Is it just one line of code, or is it dozens of components? How available is a defense in depth? How versatile is the problem? Is it a very specific problem, or is it a very broad problem? How do I mitigate? Where do I mitigate best, and where do I have assurance? Where's the best place? So many dimensions, completely different classes of bugs or threats, and not easy to find with just one tool. So that's pretty clear to me. Before we go into a better approach of how to solve this problem, I will very quickly, really very quickly, go into what tool types exist and how they work very roughly. So there's static application security testing, dynamic. I'm not going to go into interactive because that's a type of dynamic testing, and a bit of software composition analysis. So static application security testing scans the source code. It's not scanning your running applications. It scans the source code. It sometimes, depending on the language, it compiles the source code into an abstract syntax tree, right? It's something like this. Basically, all the ways through your code, from the source to the sink, and it tries to detect whether there's a problem in between. So the approach is input. Input could be something like an HTTP request that goes to your microservice, way through your code, and a vulnerable sink. And if there's no protection against a specific problem on the way, it's going to flag this specific path as vulnerable to SQL injection, for example. So a sink could be an SQL statement that is, sent to the database. The advantages are that the results are reproducible. Same source code base, same tool, same version is going to yield the same results. You have good horizontal coverage, so your own code is covered pretty well. It covers only your own code and not other parts of the stack. It can only detect a limited set of vulnerabilities. I think that's pretty clear. And it lacks context when scanning microservices. That's also a disadvantage. Let me give you an example. Let's say we have a monolithic application, and we're scanning that. Here we have the source in the UI, there's an HTTP request coming in, it goes through the business logic, and somewhere here we have the sink. For example, we have the SQL statement. So if all of that is within the same trust boundary, remember that word, it's used in threat modeling a lot, then it's easy to detect that this is a problem. However, in the microservice architecture, if I scan this service here on the left, the source might be up here, request goes to this service, then to the other service, and here's the sink, right? If I just look at every microservice separately, I'm never going to detect source to sink the problem, right? Because I'm only looking at a very small part of it. Also, if I scan this service here, for example, everything that comes in from the outside is considered untrusted, although it might not be untrusted. It might be coming from the other microservice that is developed by me as well. Right? So it tends to have a lot of false positives in such an environment. There's also dynamic application security testing, or in short, DAST. It scans a running application, and the approach is not source to sink, it's request response. So it's going to send a manipulated request to the application, and depending on what it gets back, it flags it as a problem or not. It heavily relies on known good requests, so requests that have data that actually do something meaningful. Let's say I get a request that fetches the profile picture of my thumbnail, of my profile picture. So a thumbnail of my profile picture. Sorry. We have input validation on the backend, and the logic is going to say, is this the size that we're specifying here, so 200 pixels, is this the original size, or does it have to be scaled? If it's the original size, I just read the picture from the file system and I give it back in the HTTP response. If it's scaled, I'm going to ask the scaling microservice, of course, right? Now, if the dynamic application security testing tool that scans my running application does not have the information that the thumbnail width is there, and it has to be valued between 100 and 1,000, it's always going to be stuck at the input validation, right? It can't know that thumbnail width is an integer. It will try anything, but it might get stuck at input validation when trying different attacks. So that scaling microservice back there is never tested because that request never reaches that microservice. So make sure to really take time to teach your DAST tool to really step through the application and do requests that really make sense. Advantages, it touches more parts of your stack, right? It has more of a vertical coverage. It also tends to have less false positives because it has more context through your stack. Disadvantage is that it can only also detect a limited set of vulnerabilities. That's the same for all the tools. Also, single-page applications require heavy lifting, so you need a headless browser that simulates the single-page app in order to come up with known good requests. And hard to get good code coverage because you have to authenticate, authorize, you might have to take different roles to see different parts of the UI, to test them, and so on. So DAST is really hard to get good code coverage. If you have DAST, measure code coverage and tell me the number. I'm curious. I'm sure it is lower than you think. So thinking about SAST versus DAST, SAST has a good horizontal coverage, your code. DAST, dynamic application security testing, has good vertical coverage, but it will almost never get to 100% horizontal. Keep that in mind when trying those tools. Software composition analysis is a special thing in this regard. It's a separate category. And it keeps an inventory of your dependencies. So for example, let's say you have Maven or Gradle, and you have a list of dependencies in there. It checks them for known problems. Also for license incompatibilities and other things, but important for security people specifically, known security problems. You can see dependency check. That's an open source tool for just that purpose. That's an example result down here. In general, when you look at those tools, they can detect security bugs and not threats. So they cannot detect design problems. They know that injection is bad, for example, SQL injection is bad, but they don't know that this user must not see this data set, right? Because they don't know. It could be a public API that you're accessing and there's no access control, but it's supposed to be like that. Or there could be this order request where there is supposed to be access control on an object level, right? The tool cannot know unless you give it a specification. Yeah, so design flaws cannot be detected. So when you look, this is a very rough estimation of myself of how well reliably automated tools can detect the top 13. And when you step back a meter and look at this list without reading each one of those, I can see just very few green ones, right? 2 green ones that can be reliably detected. The others are either close to impossible to detect reliably, or it can cover some aspects if you look at those tools. So that's really bad, isn't it? What can we do to do better? Vendors are going to claim that we cover the OWASP top 10. I can tell you, no, they don't. Give them the link to this video and let them browse through it, and then let them rephrase what they said. They might be covering specific aspects of each of those bug classes, but they will never be covering all of the aspects reliably and fully automated. I'm not talking about somebody, configuring the tool so that it covers that specific thing or changing a rule set. No, out of the box, give it a URL and press the play button. What's going to happen? I once talked to a SaaS vendor. Their tool looked pretty promising, and it still does. And I said, "You're claiming that you're covering the OWASP top 10. Do you know this is bullshit, or do you not know?" And he said, "I know it's bullshit." He said, "All the other vendors claim the same thing on the website. We don't want to be the only ones not claiming to cover them, because this is what management is looking at." And I was like, oh, really? So they put this on their websites because the others do it as well, but they know they can never reliably cover that. Be aware of this potential false sense of security that comes with that statement. They can't reliably cover them. They can't just reliably cover some aspects of it. A more sustainable approach to go about this problem. I'll take you through a concrete example. Okay, we talked about single-page applications, and I'm taking one of the most popular SPA frameworks, Angular. Okay, so single-page applications are good for security in general because they introduce a good separation of concerns. They completely separate everything that's presentation, interaction with the user, from the business logic and so on. So it's not one huge code base. We have a separate thing that has one responsibility. For single-page applications, only a small set of vulnerabilities is really relevant. So looking at the OWASP top 10 or even that combined list, it's only injection, because cross-site scripting got a part of injection in the OWASP 10 2021. But it's mostly cross-site scripting. There isn't really any other really prevalent security problem that's only the single-page application's responsibility. There are things where it's involved and all, but it's mostly cross-site scripting. How can we screw up? Those of you who use Angular, it's bypass security trust something, and the direct use of unsafe DOM APIs, whatever it means. Let's have a closer look. So let's suppose we have this JavaScript code on the front end. This is the HTML, and this is coming as an input from a potential attacker, right? And that attacker specified an image tag that executes JavaScript code because it does alert one on error, and that error is going to fire because source X does not exist. So in my Angular template, I do this. I create a span. I do inner HTML. Inner HTML being the most important DOM cross-site scripting sink. All right. And I take that variable HTML and then I put it in there. So you would suppose that this code is going to execute because inner HTML does not change that HTML visually in any way. Using inner HTML in JavaScript just directly puts it in there. And if it's JavaScript, it's going to execute it. If it's a script tag, it's going to insert it. If it's an image tag, it's going to create it, right? So it just puts the HTML as HTML and also JavaScript in there. The good thing, however, about Angular is that Angular sanitizes this. So what's left is just that. It strips out everything that could potentially contain JavaScript code. That is nice. That's really nice. Let's have a look at another example. You know, I'm an attacker. I started as a penetration tester 12 years ago, and I'm used to trying to find those tricks and bypasses. So a link, an href attribute of a link can also contain JavaScript code. I don't know if you knew that. You can write JavaScript colon and then JavaScript code. So if I do this in my Angular template, href can contain JavaScript. I would suppose that that JavaScript code is executed in the moment this is rendered, right? Again, the link coming from an untrusted source, such as an input from a potential attacker. Is this going to execute? No, because Angular sanitizes this. This is awesome. Angular is really good in terms of protecting itself against cross-scripting attacks, and you really have to screw it up hard to bypass this thing. So what it ends up being in the DOM is unsafe, semicolon, JavaScript, whatever. And when the href starts with unsafe, of course, the browser is not going to execute it because it sees it as just a usual relative link. Also. Okay, so we know the technology. We know Angular now. We know what cross-scripting means for Angular. Usually, it's really hard to screw up, but there are ways to screw up. So the next thing we ask ourselves is, how can it still go wrong? Well, with this. So it's mentioned as a security risk in the docs, but still, it could go wrong. You can do bypass security trust HTML, for example, and then take that untrusted input and put it into your DOM, and then it's going to execute that code. You need that, if that thing can actually contain JavaScript, which it shouldn't. This is a design problem if you have it this way. But these are ways to screw it up. So these are ways, if you have this in your source code, if you're an Angular developer, go into your IDE right away, press Control, Shift F, and search for bypass security trust, and fix it today if you find it. So there are ways to screw up. So how can we find this problem with automated tooling? Well, there is tools like linters. Linters are just static analysis tools, basically. And there is a specific rule out there by Microsoft, not sure when this was updated the last time, 2020, okay. So you can configure the linter to find bypass security trust something. Right? That's a good idea, because then even though a new developer on the team doesn't know that they need to watch out for cross-scripting, it would still catch it. Is there a good defense in depth? Yes, there is. As I mentioned already, content security policy is a mechanism in browsers to enforce certain security rules in applications. So if you set this as a response header, for example, in your application, the browser is not going to execute inline code, and cross-scripting attacks are most of the time is JavaScript code inside HTML inserted by a malicious attacker. So this is a really good defense in depth mechanism. Yeah, it's even documented in the Angular docs, so they natively support this as well. So what is this more sustainable approach that I think is better than just buying a tool with hundreds of thousands of dollars and throw it at my software in terms of static analysis and dynamic analysis? I think the thing you should start with is determine the impact of security incidents per system. So you might be dealing with 10 or 20 or 100 different pieces of software in your company, but not each one of them is equally important, right? There could be software that's publicly available on the internet and other isn't. There could be software that processes sensitive data, other does not. There could be software that has hundreds of thousands of users and also hundreds of thousands of potential attackers, and others that are just used by 5 people on an internal network that is separated from the rest, right? So depending on that, you might want to do this approach, or maybe just prioritize it down. Document your tech stack. So you need to know what we're dealing with, as we could just see. Determine the relevant vulnerability classes for each component. So you could take the OWASP top 10 as a starting point and say, this is relevant, this is relevant, this is relevant, and then find out for each one of those bug classes, how does technology help? What could still go wrong? Which tests would cover those bugs? Is there defense in depth? And is there a risk left? Could be a simple table, right? And then you document this for each of those bug classes. This is way more targeted, because then you can say the mitigation of this bug class is better done with static analysis. This one can't be caught by static analysis, so I need to do a regular penetration test. This can't be caught with static analysis, so I have to maybe do a code review. But this and this and this one can be reliably covered with static analysis, and we tested them, and this tool does it. The other two don't, right? So it's way better to look specifically at the tools for specific bug classes rather than just throw it at the software and see what comes out, because you're gonna be hit with millions of findings, and you cannot distinguish the signal from the noise. All right, so wrapping this up, key takeaways of this talk. Vulnerability classes are not one-dimensional. They are really, really, really different in many aspects, as you can see. One tool won't do the job, even if the vendor claims so. I'm not saying don't use tools. I'm saying use tools, do it, but only once you know that they're going to solve your problem. Really test them for specific bug classes. Introduce the bug, scan it, and see if it can detect it. Document the relevant classes and link them to mitigations on the appropriate levels. Could be implementation, could be configuration, could be design, could be process, could be automation, whatever it is, right? Could be penetration test every year. And in general, knowledge and awareness about those problems, and you will have to learn this in order to understand whether it is a problem in your environment or not, is really key to going about those problems. And you're here today, so that tells me that you want to learn about those things. Yeah, so these are the key takeaways.
I'd like to ask you one. Would you generally advise against using any automated tools, like you said, the DAST?
No, not at all. So I would just generally advise against taking a tool and just relying on because it costs $50,000 a year. It must be a good tool. Let's just throw it in our software and see what it does. This is what I advise against. I would really advise to make yourself aware of the specific problems you want to solve, and then test them really. So if you have an Angular application and you want to use a static analysis tool, introduce a cross-scripting. That's a good exercise also to know what it looks like. Do bypass security, trust HTML, have a vulnerable template, vulnerable input, malicious input, and exploit it, test it. Yeah, it works. I can attack the application, and then take that source code and throw it into the tool and see if it can detect the problem. So I'd really just not ask you to. I'm not saying tools are bad. I'm just saying they sometimes claim more than they can really do. But in general, there are lots of good tools out there. Just look at what do you want to protect yourself against, and can the tool really find those specific problems? This is what I advise.